Hi, welcome back to geology. So we are at the point where we have gone through and talked about igneous rocks and the process of that heating and melting of lava and magma to then solidify and create and crystallize into a new igneous rock. And we can have intrusive and extrusive. We've talked about sedimentary rocks and how we can have different types of compaction and cementation of material to get either organic, detrital, and or chemical sedimentary rocks. And then finally, we're at our last rock in our rock cycle, which is metamorphic, which has to do with lots and lots of pressure. So we have heat, pressure, and then chemical changes. Metamorphics are kind of like a combination of all three. You can metamorphose an igneous rock by changing it, and you can metamorph a sedimentary rock and change it, and you can metamorphose a metamorphic rock. So I always think of when I was growing up, Teenage Mutant Ninja Turtles. They metamorphosed. They were turtles, and then all of a sudden they drank the evil green juice, and then they became super ninja turtles. And so metamorphic rocks are kind of like that. They can change. They can metamorphose into something else, and so that's where that term comes from. So let's get started here. So metamorphic rocks in general always form with three different types of processes that have to be available. The first one is heat, meaning that there has to be some type of way to either bake the rock to make it warmer, or there has to be some kind of magma chamber there that's going to heat things up, or it's going to be close down to the asthenosphere, where it's going to be really close to that convection cycle that's causing plate tectonics that we'll talk about later. We haven't gotten there just yet. The other process is that it can be exposed to a huge amount of pressure, and that can happen in either mountain building processes, once again with plate tectonics, or just being buried deep down and have a whole bunch of other layers kind of building on top of it. And then finally, that last way in which metamorphic rocks can be changed is due to hot fluids running throughout, and it will chemically change the rock. So heat and pressure and hot fluids are the three different ways in which we can change a rock to become metamorphosed. Two types that occur on Earth's crust. One, which is occurs in small volumes of rocks, come in contact with magma. So once again, we're being exposed to some type of heat processes. The magma doesn't totally touch that rock, though. It's just there at a point where it's just heating it up. So kind of think about like an oven, and then you put something in the oven and it changes it. So like cake batter, for example, you put all the batter and mix it all together with eggs and milk and sugar and the bread and all that kind of things. And then it's almost like a liquid goo, but then you put it in the oven and the oven heats it up and changes it. It metamorphoses the cake batter, if you want to kind of think about it that way. Same idea is that, so there's some kind of magma chamber that might be there changing the rock. The other occurs in large areas that are affected by heat and pressure. And this is going to once again kind of be that idea of some type of plate tectonics, which I know we haven't talked about, but you've probably heard it before in either your middle school years or in integrated science when we talked about our three different types of boundaries, which is convergent, divergent, and transform. You are mostly going to see a metamorphosed rock in either one of those convergent and sometimes divergent boundaries. Lots of this happens in our convergent boundaries, though. They're just super active. So those are different ways in which we can see it. So our first type of metamorphism is called contact metamorphism. So as you can see, this down here is a magma chamber or a batholith that you might remember from our igneous unit, just a huge blob of magma that is kind of hanging out below all these other layers. So these are more likely, with the way that they're striated, is our sedimentary rock. So we can see that. So this area right here, that where it says contact metamorphism, is this magma chamber is literally baking and heating up this rock zone here, and it causes a chemical change in those sedimentary rocks or it could be igneous too, but the way that I can just look at these layers here, those are going to be sedimentary. So magma comes in contact with existing rocks. It heats from the magma chamber to change this area. And this is a really, if you've ever able to actually see a real example of this, it's called the scarn zone. Think of it as a scar, is that this magma is burning this rock. And with it, these rocks are being changed chemically, and lots of time these scar zones are going to make these huge, big crystals. And so there is a lot of gemstones that can be found in this scarn zone. So once again, this is going to be an active region that is normally going to be found in our zone that is going to be closest to probably a convergent boundary where the plates are coming together. Some type of magma source has to be there. Regional metamorphism is a huge scale. So contact is kind of small. Regional is going to be on a super large scale. So it could be happening like all along a plate boundary or a mountain region or whatever it may be. So this rock here is an exposed metamorphosed rock. It's actually called something called gneiss with a G. It does look like a nice rock, but it's actually G it's a German name. So large area of rocks are affected, normally during plate tectonics or mountain building. And so once again, just think a whole region is being smashed together or pulled apart, and it causes these rocks to kind of take this tremendous shape too. More than likely, these were at one point sedimentary rocks that just laid really, really flat. Actually, I'm going to go like this way so you can see it. And then something came along and smashed them, and then they got all bent and crooked. So my fingers aren't doing a good job, but they get kind of wavy, and those layers were once flat, and then it gets kind of broken and flat and moved all around. Classification of metamorphic rocks. So two types of classifications, foliated and non-foliated. And the best way to think about this is lines versus no lines. And that's all that it means. It's foliated, rock textures in which mineral grains are arranged in planes or bands. Here's that word, nice. I always used to joke in class, it's a nice rock. It's a geology joke. I'm sure if you look up a meme, you'll hear it. That's a nice rock, meaning that, once again, we can see the lines, we can see the striations. This is probably actually once a igneous rock, so we'll talk about this here in a few minutes, is that metamorphic rocks normally have a parent rock and a daughter rock. So granite would be the parent rock, and it had big chunks of crystals, and it got stretched out, heated and then stretched out, and then it becomes metamorphosed into gneiss. And we call this foliated. Non-foliated, it just means that it does not have bands or alignments. It was heated up, and then when it chemically changed, it resolidated into something that looks a little bit different. This is actually quartzite, which is a form of quartz that's been chemically changed. So what happens is that we can have different types of pressures that really affect rocks as well. So especially in those tectonic plate boundaries, we can have huge areas that are completely deformed and transformed into metamorphic rocks. And the biggest one is hydraulic and direct. Hydrostatic is going to be something where the pressure is coming from all sides, so it's being pushed this way and this way. Whereas direct might be kind of what I was just doing earlier. Like, here's my hand again, and that would be direct. If I wanted hydrostatic, it would be pressure from all sides, kind of like it's being crunched in. Whereas direct is just normally one side or the other. With metamorphic rocks, there's a couple of different things that we'll be looking at, mostly looking at how pressure and temperature changes. So don't freak out when you see this chart. But these are our facies series, which just means that if it's underneath a certain temperature and pressure, this is the type of metamorphic rock that we're going to get out of that. If it is this pressure and temperature, this is the type of metamorphic rock we're going to get out of it. Very similar to Bowen's reaction series, except that we've added pressure, temperature, and depth in the Earth's crust. So we have 3 points that we're kind of looking at here. So for example, if I'm looking at a pressure of 6, and then let's say I'm also looking at a 300, let's go 500, I like green, and then an approximate depth of 20, I'm going to be looking at a contact rock that might have more of our green type elements in it. And I'll explain, what that means here in a minute. So it's just the idea that it's kind of changing. But what I really want you to understand is that pressure, temperature, and then depth. Where is this rock at? Is it close to the surface, which means it's not under a lot of pressure. So that's going to cause the minerals to be different. So think back to Bowen's reaction series. We have more silicate up here at a lower depth, and then a higher depth is going to be much more of our hornblends and pyroxenes and other really dark mafic type minerals. So in order to figure out how a metamorphic rock is categorized, we use what is called a ternary system. And if you've had geometry, you've probably seen something like this before, where we're going to look at percentages of how many minerals are found in one area, what is the percentage found in another, and then finally the third one, how many we can have. So if we look at this area here, we've got several different markings kind of put together. And how we would read this is that if we're looking at how much of mixture C is in this period or this pyramid right here, we're going to read these lines that run this way. So we're going to be looking at the 20. And then if we are looking at A, you can see the red lines running this way and then the green lines here. So this one would be like 20% of mixture C, maybe about 10% of mixture A, and then about 80% of mixture B. So if we add that all together, 80, it should equal up to 100, which that doesn't work out very well since this is not 80, 90, 100 would be right there. So we'll have to double check that. We're going to practice with some ternary diagrams though, but the idea is that it should always equal up to 100%. But the biggest thing, once again, I want you to take away from our metamorphic rocks is that heat, pressure, and hot fluids, and then we can have foliated and non-foliated. And we'll spend some time looking at those ternary diagrams here in a little bit. Hopefully this was helpful. Thanks.